the screen clearly?
Yes, sir.
Okay, consider the system described by the XY relation as follows. Y is equals to YT YT is equals to T squared XT. Okay.
Yes.
So we want to find out if this is linear. So another thing now we want to find out if it's linear. Okay. So just assume you have an input x of t, and then the output oh, those guys who are just coming down, please don't make noise. Keep your mic muted unless you want to say something. It's t squared xt. Okay. If there's an input xt, the output is t squared xt. Agree?
Yes, sir.
Okay. So now we want to find out, determine, we will test for linearity by using the principle of superposition. Test for linearity by using superposition. Okay. Input xt produces an output. Input xt produces an output of t squared xt. Therefore, input A1x1t should produce t squared A1x1t. Correct?
Yes.
Just rewriting this is going to be A1 t squared x1t. Okay, now I can call this. I can call this y1t. Input xt will produce an output of t squared xt. So we're going to test if this function is linear. We're going to test for linearity by using superposition. Input A1 x1t will produce an output of t squared A1 x1t. Okay, if you note very carefully, I can call this part t squared x1t as y1t. Similarly, if you have another input, A2x2t, and that's going to produce t squared that's going to produce T2 A2x2t, which is going to be A2x2t.
Yes.
And I can call this y2t. Okay, any question?
No.
Okay. Now we can see individual output is producing an individual, individual input is producing an individual output. So if I sum the individual input, if I input the sum of individual input from the previous case, so you're going to get an output that's going to be t squared a1 x1 t okay. The individual input produces an individual output. Individual input produces individual output. So now I sum the individual input. It's going to produce a sum of individual output. Rearranging things, I can rewrite this as a1 t squared x1 t plus a2 t squared x2 t. So we note this is your y1 t and this is your y2 t. Thus, I can say that a1 x1 t, the sum of inputs a2 x2 t produces a1 y1 t plus a2 y2 t. Thus, this is linear. The system is linear. When you sum the individual inputs, you're going to get a corresponding individual output. So this is the proof, superposition principle, proving that this is linear. For example, let's say if you get something else, let's say in addition to this, if you get at the output another term, like for example, t squared or something, and then it's not linear. It's not linear. Maybe later we will look at, we have done some examples in the class where a system is nonlinear, and you know how the output looks like. You guys have any question?
No, sir.
Okay. Next one. Okay, I'm going to go through quite quickly. We'll try to finish in about 15 minutes, not 15 minutes, 50 minutes. Because the videos, when I watch the video, looks like I'm going very slow. Maybe you guys might be bored looking at the video. I don't know. Maybe I can run if you feel bored, you know what you can do? You can run the video faster at YouTube. So it goes quickly. So
Okay,
if
sir.
anybody feels, okay, but you know, I want to go faster at the same time, I want to go slow enough so that people can understand. So if anytime, if you're not understanding anything, you just stop and ask me. So the next thing is this time invariant? Is this time invariant? Okay, to prove that, remember, maybe you might have forgotten from our class notes. Maybe those guys taken this before. Something is time invariant if the delayed input yt is equals to delayed output yt. So let me see what I'm trying to say here. If I go and delay the input, let's say if I go and delay the input by t naught, going back to that equation, yt is t squared xt, right? Yt is t squared xt. If I delay the input, on the left hand side, I'm going to delay the input. And that means I'm going to delay this. I'm just going to delay this part. Replace t with t minus t naught. Okay. I'm going to replace t with t minus t naught. So that's going to give me only the t, that's only this t, only this t. Only this t and this t. So I'm going to delay this t is equals to t squared. So actually I'm delaying the input by t naught. I'm delaying the input by t naught. So the output also is affected. Okay, I'm just delaying the input by t naught. Just replacing the t with t minus t naught. And that's going to replace the output by t minus t naught. Do you guys follow this part so far? So this is called input delayed yt. This is called input delayed yt. Next, look at the output delayed yt. Output delayed yt, you're going to delay the output. So this is your original, okay, let's put here. So okay, this is your original equation. So now I'm going to delay the output, delayed yt. So this is the output, right? The output is here. This is the output. I'm going to delay this. Okay, that means I'm going to replace the t with t minus t naught. Replace the t with t minus t naught. So I'm going to replace every t here with t minus t naught. So when output is delayed by t naught, everything is affected. Every t is affected. Every t is replaced with t minus t naught. Let's call this output y dt. This is the output delayed y dt. This is the input delayed. Is the input delayed output equals to output delayed output. Okay, what was the output delayed, input delayed output? It was t squared xt is equals to output delayed output. Are they the same? Is the left side equal to the right hand side? Are they the same, guys?
Oh, yes.
Huh? No, see, the left side is t squared xt. On the right side, the expression is different. So they are not the same.
Oh,
Huh? Can you note that? Left hand side and right hand side of the equation are not the same.
hmm.
Left hand side, it says t squared. Left hand side, you say t squared xt, but the right hand side, it says t minus t naught squared x t minus t naught. So they are not the same expression. Correct or not? So therefore, they are not the same. Therefore, not time invariant. Not time invariant. Because of the left hand side is not equals to the right hand side. Therefore, the system is time invariant, not time invariant. Or you can say it is time varying, not time invariant, or it is time invariant. So this is how you test for time invariant. All you have to do, you just delay the input by t naught, and then you see what is the output. Delay the input by t naught, and then you see what is the output. Next, first you delay the input by t naught, and you see what is the result. Next, you delay the output by t naught, and then you'll see what is the result. And then you equate both of them to check and see if the expressions on the left and right are equal. Apparently, they're not the same. So therefore, it's not time invariant. If you are not used to it, get used to it. Do you have any questions?
No, sir.
No, sir. Okay. Thank you, sir. How about the other guys?
No, sir.
Okay, let's move and say find out if this system is BIBO stable, BIBO stable. BIBO stands for bounded input, bounded output. Bounded input, bounded output, BIBO stable. So how do we test that? What we do is we try to input a bounded signal and see if the output also is bounded. Okay, let's do that. So you have an input, a step function. You know what is a step function? You guys are quite familiar with this. You have a step function. Okay, this is the step function. Okay, let's say call this 1. Is this bounded input? Because somebody tell me, is this a bounded signal? Anybody knows the answer? Yes, this is a
No.
bounded signal because it only varies from 0 to 1. Okay, the lower value is 0, the upper value is 1. So this is a bounded signal. So we're going to input a bounded signal BI, bounded signal input, BI input, and find out whether the output is also going to be bounded. So what is the output is going to be like? See, the output is going to be YT is equals to T squared UT, right? And what is UT? UT is a step function. You know, this is this step function. Okay, T is equals or greater than 0. Why is it so? Because it is defined by the step function. Okay, it's defined by the step function. Can you see below 0? The signal is 0. Above
Yes, sir.
0, the signal is 1. So if I sketch this signal, it's a T squared. So this is going to be just T squared. So this is going to be T squared defined for T is equals to greater or equal to 0. Usually this is T squared is a parabola. It's going to be, this is a parabola. Right or not? But you must understand it is not defined on the left-hand side. It's only defined on the right-hand side. So it's only defined on one side. Okay, but this is growing. You see, growing signal. As t increases, it keep growing. So is this bounded? Is the output bounded?
No.
So therefore, the bounded is not output for a bounded input. So therefore, this is not stable. Is this memoryless? Is this memoryless?
Not
Okay,
sure.
if the output, okay, if the output, this is if output depends on pass input, then it has memory. Then it has memory. If the current output, maybe let's put current output. If the current output depends on the past input, then the system has memory. Okay. If the current output depends on future input, then the system has also memory. If the current output, if the current output depends on current or present input, then it's memoryless. Okay, generally, if you see in a time domain, this is like, for example, time axis, you have 0, 1, 2, okay. It depends on where you are standing. You know, if you are standing here, let's say if you're currently standing here, then when time t is equal to 1, if you are standing at time when t equal to 0, then time t equals to 1 is future, right? When then the time when t is equals to -1 is past. Okay, so this side is like past, you know, for example, this is like past. This is like future. This is just a general statement to make you understand what it means by past input, present input, present input is not necessarily 0. It depends on where you're standing. You know, if you're standing here, then the present input is 1, right?
Yes, sir.
Okay, so let's say if I am standing at 1, and then I will, okay, my current output, where T is equals to 1, my current output at 1 is equals to X of 1. And now you can see very clearly your current output depends on present input. Present and current, they're same thing, right? So
Yes.
this is memory. Current output. Current output Y1 depends on present input. Depends on X1. I made a lot of notes on this. You can, maybe you might have forgotten, but let me give you a small example for a case where the system has memory. For example, just to clarify if you're still confused, for example, system with memory. System with memory. Okay. For example, let's say you have yt is equals to x minus t. Okay, I'm going to find out what current output. Let's say my current output depends. Let's say my current output as t equals to 1, my current output y1 is equals to x minus 1. I'm just replacing the t with 1. So you can see now your current output depends on past input. Past input, negative. See the timeline here is past input. So is the memory, and now next question is this causal? Causal. So you have funny terminology in signals, but you're not going to see this all the time. Unless you become a DSP engineer, maybe you have to deal with them. Depends on what you're going to do. Okay, is this causal? Is this causal? Causal means if output depends if your current output depends on present or past input, then it's causal. You already, it is maybe from the previously that we did here, right? Remember? I'm bringing this over here. The output depends on the present input, right? Present input. Present input, but it doesn't depend on the past input. But here, what it says is, if the output depends on present or past input, then it's causal. So we know that it's already depending on the present input, so it's causal. Any questions?
So far, no, sir.
Okay, good, sir.
Yes, sir.
Huh? Cheers, sir. Okay, thank you. Okay, let's go through this. I think you'll get something like this. I'm sure these are all past years questions. So you need to, I would like you to write an equation for this signal. What is xt? Xt, you know, there's a, if you, this is a sinusoidal signal. The signal can have a DC offset and then plus an amplitude. It can be cosine or sine. It depends on you, how you want to do it. You can write in terms of sine or cosine. Let's say if I decided to write this in terms of cosine, then you must have frequency times time, or plus or minus theta or phi, whichever. You know, just call this phi. So you should find out all this information. You need to find out how many. You need to find out this. You find out the amplitude, and then you have to find out the frequency. You have to find out the phi. There are 4 things that you need to find out. 4 things that you need to find out. Okay.
Clear,
First,
sir.
before, okay, so before I move on, you know, I want to show you just a small review, just a small review on signal, sinusoidal signals. So, you know, as cosine signal looks like, right? I mean, it's not coming out right because my graphic tool is not very good. Okay. Okay, this is cosine signal, you know, cosine. This is cosine omegas of t without any phase shift. Can you recognize this? This is time axis. Okay, this is the amplitude axis. Amplitude, cosine or sine or whatever. And then sine, okay, look, can you, between sine and cosine, there's 90 degrees phase shift. 90 degrees phase shift. So you guys should be aware of all these things. Okay. So in this, if you look at this, this one, can you tell if this is a cosine or sine? you cannot tell because there's a phase shift here. You can either treat this as a cosine or sine. When you write it now, if you want to be a cosine, but you must be aware between sine and cosine, there's a 90 degrees phase shift. But if I were you, I'll go and see which one is, see the cosine usually start from here, right? Cosine start here. But sine is far away from here. So cosine is very close to this. So we can assume this is a cosine wave that has been phase shifted. Okay, so it's up to you. But I just wanted to do this review. Like for example, in this case, cosine omega t is equals to same as sine omega t minus 90 degrees. Okay. If you want to verify that, then you try to plug in some values for omegas of t. 0, omegas of t is equals to 45 degrees. Then omegas of t is equals to 90 degrees. Try to plug in this into both the equation and see they should give you the same answer. So cosine 0 is equals to sine 0 minus 90 degrees, right? 0 minus 90 degrees, cosine 0. Are they the same? Is cosine 0 same as cosine sine 0 minus 90 degrees? Hello?
Yes.
Can you guys? So you guys, when omega t is 0, cosine of 0, is this equation right? Is cos omega t is equals to sine omega t minus 90 degrees? They're not the same, right? Sine 0, sine 90 degrees. So should it be plus or minus? So both of these will give you 1, right? Cosine of 0 so it's 1, sine 90 degrees is 1. So what is cosine 45 degrees? Is equals to sine 45 plus 90 degrees. You see, also will give you 0.707. Cosine 45 degrees is same as sine 135 degrees.
Yes.
And then when omega t is 90 degrees, you get cosine 90 is equals to cosine 90 is equals to sine 180 degrees. Both of them will give you 0,
0.
right? Okay.
Yes.
So that's how you check. Earlier on, I put minus, it didn't match. Minus is when you solve for this, omegas of t plus 90 is equal to 0. Omegas of t is equal to minus 90 degrees. Okay, so that's the relationship. So I would like you to keep this in mind. Either you can write this in terms of cosine or sine, but if you write in terms of sine, then you must should plus 90 degrees. Should be aware of this, just for your information. So first of all, let us find the DC offset. DC offset, how do we find the DC offset? To find the DC offset, what you can do, first you find what is the peak-to-peak value. What is the peak-to-peak value? Call this peak-to-peak. Just call this X peak-to-peak. X peak-to-peak is, I'm not talking about that pig in the jungle. Peak-to-peak. X peak-to-peak is, what is the highest value? 2, right? The lowest value is -6. So peak-to-peak is 2, highest peak, lowest peak minus 6 is equals to 8. So then what is the value? So you have as a wave here from peak to peak, the value is 8. Then what should be the value of this, let's say this wave from year to year is peak to peak. From year to year is 0 to peak. We call this just XP, 0 to peak. XP is 8 divided by 2 is equals to 4. So any problem here?
No, sir.
You guys understand so far?
Yes, I understand.
Yes, sir.
Okay, this is from
Yes,
here. Peak
sir.
to peak is 8. 0 to peak is 4. And now we come to this wave and you see the peak. If this wave is centered properly, it will see the lower value is -4 and the upper value will be 4. Okay, but now because there's an offset, DC offset, so the lower value and upper value, they are not, the amplitude is not the same, right? The amplitude is supposed to be the same. The peak value is for 2, the negative peak value is -6. So how can I center it? What is my DC offset? In another question, another way is, since I know 0 to peak is 4, but here you see the 0 to peak is only showing me, sorry, the the 0 to peak, okay, yeah, 0 to peak is only 2, right or not? How to make this 4? You must add 2, right? You
Yes.
must add 2. Okay, so your DC offset is 2. Okay, if you DC offset, then it will be swinging from -4 to +4. So the DC offset is 2. Excuse me. Next, what is the period? Something already moved from here. I need to undo this. See, the thing moved here. Okay. So what is the period? There's many ways of finding out the period. One way is to go and find the time from peak to peak. That will give you the period. Or you can find the time from negative peak to peak. That also can give you the period. Or you can find the, you cannot find the period. Now you can see, look for a center value, center from year to year. It's a 0, -2 crossing. Because there's a two, from year to year, you also can find the period. Okay. You look for the easiest, excuse me, the easiest way to find, I think, is this place here. This is the spot. I can tell you it's around 2 seconds by just looking at it, right or not? Do you know why? Because from year to year is 2, right?
Yes.
From year to year is 2, isn't it? And then I see, like from year to year, there's a slight shift. There's a slight shift. And then there's a slight shift to the right. So they are about 2 seconds, I can tell. I don't know if you guys can see that. Right?
Yes, we can, sir.
So you don't have to be accurate, you know, but you have to mark in the diagram how you find it. Okay. So time is 2 seconds. Sorry, period is 2 seconds. Period is 2 seconds. Once you know the period, you can find the frequency. Frequency is 2 pi. Frequency is what? 2 pi over t, right? 2 pi. Frequency is 2 pi over t. Is 2 pi over 2, which is pi radians per second. What else we need to find? So we need to find, and then you see, there's one more thing we need to find. So if I assume this as a cosine wave, let's say if I assume this as a cosine wave, cosine wave slightly shifted to the left, slightly shifted to the left by delta t. It moved slightly to the left because cosine usually begins here, right? Cosine begins here. And now it did this point, it's moved to this spot right here. Do you guys can see that?
Yes, sir.
Yes, sir.
Yes, sir.
So now I can I approximated, you know, because from year to year is 1. So maybe it's around 1/3, maybe around 0.33. But I think it's slightly bigger than that. So you don't have to be, you know, very accurate. You can roughly approximate that shift to be around minus 0.35 seconds. I put minus because shifted to the left. But if you just wanted to say a change, that's fine. 0.35 seconds, approximately. We put 0.33 is fine. Since it's shifted to the left, the delta t, I'm going to put a minus sign, 0.35 second, because it shifted to the left. Shifted to the left. So that means I can find my phi. The shift in time, you can convert that to shift in pi, or radians, or degree. we know the phi is omega t, right? Frequency times time. Okay. Frequency we found out is pi. Time you found out is 0.35. So that's going to be minus 0.35 pi radians. Pi radians. So we got all the information that you need. Now we can write the equation. xt what was the DC offset? DC offset was 2. And what was the amplitude? Amplitude was 4, right? 4 cosine. Maybe I should bring this over here so that you can see this clearly. Okay, now can you guys see clearly?
Yes, sir.
Yes, sir.
DC offset. Okay. A is 2. Sorry, A is 4. DC offset is 2. And then you have cosine. Omega was pi, right? Pi. T is T. T is a variable. You cannot plug in any numbers for that T, okay? Now we have 0.35 pi for phi. Okay, it's minus sign here, but it's plus sign inside here. Okay. Because you know it's pi t plus 0.35 pi is equal to 0. Therefore, pi t omegas of t, same as omegas of t. Pi t, when you solve for pi t, is going to be minus 0.35 pi. So that's why when it comes inside the bracket, it becomes positive. Okay, we are already done with I already omitted one of the question. I'm not going to, so I'm already done with the midterm 2000 March, done.
Okay.
March 2018 exam. I went through that. Now I'm going to do I'm going to start March 2019 midterm.
Okay.
Okay, just midterm is your reference. Once you know how to do this, then your midterm 2020 is going to be easy.
Yes.
Okay, these are problems. We already done this before. We are doing this again for extra practice. Remember this? So this problem actually is good for you. You can get more practice. Question. We have done this before, right? Periodic or not periodic and all that thing.
Yeah.
So the first question is this periodic or not? You look at this carefully. ET, cosine, I can tell before doing anything, I can tell you this is not periodic. Because you know why? Because of this. Because of the exponential function. This is an exponential function, right? And this function is going to grow. Keep growing. So where's the period? Can you tell me? There's no period here involved. it's going to keep growing. Then if you're going to multiply this by a cosine function, if you're multiplying this by a cosine, which is sinusoidal, which has period, okay? But you know, this is going to go like this. That also is going to grow. Overall, there's no period. And then you have a DC here. If you add the DC, all it's going to do is going to make the, it's just going to add more to the, it's going to make it, probably maybe it's going to do a DC offset. That's all. So overall, it's not periodic. So you don't have to, you can also do your own reasoning like this and say it's not periodic. Can you guys see that?
Can, sir.
Yes.
Xt is e to the minus j omega t plus e to the j omega t divided by 2. Running out of battery. Good.
Oh,
Okay, this is, you know, this is using Euler identity. Using Euler identity. This is simply cosine, cosine 2t. Let me look at the question again. So according to this Euler identity, this is equals to what? Excuse me. Cosine. See, there's a problem with this question. Omega is not given, right?
yes.
Although omega is not given, but you can tell easily it's periodic. It's just going to be cosine omega t, right or not? It's just cosine omega t.
Yeah.
It's periodic. It's a cosine function. There's only one frequency, so it's periodic. Okay, guys. Do you all remember the Euler
Yes.
identity?
Yes, sir.
Yes, sir.
Okay, in the exam, I put omega is 2, but you know the omega is not given. Even if the omega is not given, and we know it's a cosine. Cosine is sinusoidal, and it's always periodic. Okay, the next one. Hello, sir. Lecture பண்ணிட்டு இருக்கேன். கொஞ்ச சொல்லி கொடுப்பா. Okay. Okay, sorry about that. So the next one is xt. pi over 2n. And this is n. This is n, you know, n. It looks like pi, right? So this n is a discrete frequency, discrete omega. Usually we have omega here. Excuse me. Usually we have omega here, but you know, this is, sorry, not omega. This is omega. Omega 1, and this is the n. And n is a discrete frequency. Sorry, discrete time. Okay, so discrete time, this omega 2 is right here. Omega 2 is 1. So this is also another discrete frequency. Discrete time. Okay.
Yes.
You don't worry about the phase shift. So omega 1 is pi over 2. Is pi over 2. So period 1 is 2 pi. 2 pi over omega 1. Two pi over 2. 2 pi over 2 is 4. Omega 2 is 1. So T2 is 2 pi over omega 2 . So T1 over T2 is 4 over pi, 4 over 2 pi, which is 2 over pi. Okay?
Okay.
Is this a rational number? So this is an integer. This is not an integer.
Not rational.
So like, you know, usually pi is like 3.1 something, right? So it's not
Yes.
rational. Okay. So therefore it is not a rational, it's not a rational number. So not periodic. Any question?
No, sir.
Clear,
Okay, I'm
sir.
just going to do, huh? Yes, sir.
No, sir. I say no, sir.
Okay, thank you. The D, so I'm going to, this is the only, this is the last problem I'm going to do. We will continue the next time, just only a few more questions.
Okay, sir.
Because the next question is quite graphical. It will take some time for you guys to finish this. So sine squared 3 pi over 2n, and plus sine 3 pi over n. 3 pi over 4n. Okay, even though there's a square here, this is not going to affect the frequency, right? This is not going to affect the frequency,
Yeah.
affect omega. So T1 is 2 pi over omega 1. T2 is 2 pi over omega 2. This is omega 1, omega 2. Pi cancel, is 4 over 3. T2 okay. So T1 over T2 is going to be 4 over 3 divided by 8 over 3.
Yes.
It's 4 over 3 multiplied by 3 over 8.
Yeah.
It's going
1
to
over
be
2.
1 over 2.
Yes.
T1 over T2 is 1 over 2, so it's a rational number. Therefore, it is periodic. And the period is the lowest common factor is 2, right?
Yes.
The lowest common factor is 2. Then you can just say 2T1. Or there's another way to do is you just cross multiply. T1 over T2 is 1 over 2. So this is going to give you
T.
2T1 is equals to T2. So the period is 2T1 or T2. They're going to give you the same answer. 2T1 or T2. Simply what is T2? That you found out earlier. T2 was 4 over 3. T2 is 8. T2 is 8 over 3. Yeah. 8 over 3. So the period is 8 over 3.
Mm.